Okay, so we're going to talk about thin films. So a thin film is a very thin layer of a certain substance. It's like really thin on the order of fractions of millimeters or micrometers. So what happens when you have a thin film is that a light beam will reflect off its top surface and another one will go through the thin film and reflect off the bottom surface. So that creates either constructive or destructive interference for different wavelengths when you look at the thin film. An example of a thin film is when you see soap bubbles, then you can see different colorful patterns on the surface of the soap bubble. And that's created by the interference of different wavelengths of light going through the thin film.
So the first factor for thin film is phase shift upon reflection. So when a light wave passes from a medium to another. So if the first medium, the index of the refraction is bigger than the second one, then there's not going to be any shift. But if the second one is bigger than the first one, then there's going to be a pi shift. And there's going to be no reflection at all if both are equal. So they're going to travel in the same medium. And there's going to be constructive interference if both are shifted, or there's going to be destructive interference if one is shifted but not the other.
Okay, so beside of the factor 1, which is the phase shift, there's a second factor you have to consider, which is the path difference. So what we have here is the wave travels more to the bottom and reflects more than the one waves travel on the top surface. And that distance is 2t. Well, it's approximately 2t here. So we see this one travels 2t more to the top one. And because of that, we have two equations that we can choose. The first one is 2t equals to m lambda. And here m, you can start from 0, 1, 2, 3. And in this equation, the wave arrives how the ascent. The second equation, which is also 2t, which is the path difference, equals to m plus a half lambda. In this equation, the wave arrives half cycle shift. So the wave arrived half cycle shifted from how they were sent. Okay, so for example, if here, from the first factor, we know there is no shift. And when both of them have no shift, then they will have, arrive at the eye, a constructive interference. So if we still want to keep that constructive interference, then we will choose this one, since the wave arrive how they were sent. However, if we want to arrive at destructive interference, then we will choose this equation. Another example, if one of them is pi shift, then here what happens is that from the index of refraction, it's already a destructive interference. Hence, if we want to keep the destructive interference, then we will choose this one, because it arrived how they were sent. If not, we will choose this one. An important thing here is that in this equation, the wavelength is really important, because this wavelength is not the wavelength that we used to calculate. This wavelength is the lambda naught over n. This wavelength represents the wavelength traveling in this material and not in air. And n is the index of refraction of the film material, which is really important. And the lambda naught is the lambda wavelength that we're talking about, the wavelength traveling in the air.
Okay, so an important application of thin films is to have either a non-reflective coating or a very reflective coating on top of another material, such as glass. So you could have a thin film of a certain substance over glass, and to have a thin film that creates a surface that's completely non-reflective, you want to make sure that what the eye sees is completely destructive interference. Whereas if you want a super reflective surface, then you would make sure that your eye sees a completely constructive interference. So why do thin films have to be so thin? Well, when you want to create a nice interference pattern, you need a coherent source of light. But natural light, like sunlight, is not necessarily coherent. It consists of little coherent bursts of light, but that are not necessarily coherent between each other. So in order to create a nice interference pattern with sunlight, you need a very thin film so it can capture one burst of light, so that one burst of light will go in, be reflected, and create the nice interference pattern. If it's too thick, then many bursts of light will come in and interfere together, and it will kill your pattern.
So it is possible to have thin films with a variable thickness, like in the lab we previously did. We used 2 plates of glass here, so we have glass,
because they said at first, right?
glass, and a thin film of air.
If it was the second, you would
And
put
the
one.
thin film of air had a variable thickness because we had an elastic around here and a piece of paper here, so we made a wedge
The first
in
right
between.
is
So for this specific situation, we know that because the index of refraction, there's a phase, there is no phase shift here, but there's a phase shift of pi.
tells you
in
where
this one.
all the possible thicknesses.
So
Yeah.
because we have a wedge
So
in between,
yeah.
we have variable dark and
So
bright
that's
fringes
the
all
brightness.
along
Now it can get even
the
trickier
glass because it's reflected.
sometimes this is called I
And
naught.
so if we want to look at the exact points on the L axis or on the glass, we describe it by X,
But
and
you
it
can think of
can
it
be
more as I
found,
single.
the
So I
dark
for a single
fringes
slit
can be
is
found
like this.
using
I
this formula,
for
because
multiple
remember this
slits
has a phase
is n squared times
shift of
whatever
pi,
you put that.
and the bright fringes
And
can be
then
found
if
using
you are
this
also,
formula.
sometimes they'll say, well, look to where you're wondering
So
about.
now to relate
So
X and T and
when
L
you
and
plug all
H
this
into this
in,
formula,
And you find that
we
say the
can
intensity is like
use
0.4
T to X
max or whatever.
H to
It's
L.
all with respect to what this
Now,
is.
we can
That's why it can be a bit
isolate
confusing.
T
If
by
you-
bringing this to
say
the
I
other
said the
side
angle
and
to
making
here was
T
like 40 degrees.
HX
Plug in 40
is
degrees,
equal
you
to
find
L. And then we
plug
can
in
bring
40
it back
degrees
into our formula here.
the
And
phi
for our
equation,
lab,
and you
we
get your
use
phi.
dark. We
Plug in 40
focus on dark
degrees
fringes,
to
so
the
we're just
beta
going to do that
equation,
for now.
get your
So
beta.
2T
You plug
is
it all
equal
in
to
and you get like
M
0.4.
lambda.
What you've just found is
Now
that this
we can
brightness
replace
is
it and do
0.4 times what the max is
HX
there.
over L
So
is
that's
equal
why it
to
can be a
M
bit
lambda.
confusing, 'cause they call that I naught. they
And
sometimes
X
call that
is
I
equal
naught.
to this.
Like, no. When we're
The
doing this
distance
equation,
on the
it's
L
all
axis.
How, as
Now,
far as this
looking
part's
at,
concerned,
if
it's
we want to
done
look
as
at the
best.
distance
You're
between
at
the
a
dark
maximum.
fringes, we
And
can
so
look
this
at
is
one
one.
specific X and the
And
other,
what's
and
limiting
then
it
so
is the part
delta
that
X
sort of envelopes
is
it,
equal
which is
to
this
X
guy. So that's why you can save
1
yourself some
minus
time and just
X
call this
0.
and solve for what this guy is. You're
We
really
can
solving
make a
for
really
where is this
simplified
dotted one
formula
at those
using
points.
this by isolating X here.
Yeah.
So
No,
we
it's
end up with X is equal to M L over 2H. So if we want to find the distance between two dark fringes, we can just find delta X. So here delta X is equal to, we can just look at the 0 on the first dark dark fringe. So delta x is equal to x1 minus x0. And to relate these together, get a nice formula for delta x. Using this, what we can do is just substitute these into here by doing m plus 1, which is your first fringe, lambda L over 2h minus m lambda L over 2h. And then you can simplify it some more. Because these cancel out, so you end up with delta x equals lambda L over 2h. So that is how you find the distance between two dark fringes using this formula.